Hello everyone, I tried to make this portal shader in Godot engine and it's pretty simple. Even if it doesn't look simple, it's pretty simple. Let me show you the secret behind this shader. Basically, if you remove this noise texture, let me copy and remove. You see it is just a simple gradient. It is darker inside and it gets lighter outside. So to this gradient we just add noise and we distort the noise and it becomes something like this. So it's no magic, it's really simple, just basic math, and we'll make this today. Let's begin. So the first step is to delete all the existing code. So we are left with the empty code and start by defining the shader type to spatial, which means that it will be applied to the 3D geometry. After that, make a gradient because it will be the base of our whole effect. So we're gonna visualize the gradient first. To make the radial gradient, first of all we need to center the UVs. If we look at the UVs of a quad mesh or a plane mesh, this part of the quad is typically at 0 0. It means 0 long x and 0 long y, and as we go towards this side it becomes 1x and 0y, and at this point it becomes 1x and 1y. So what we're gonna do, since our UV spans from 0 to 1, we need to subtract 0.5 so it centers around this. So this place will become 0, and to the left of it, it will become minus 0.5 to this end and plus 0.5 to this end. Now the thing is that why we need to do it. This is because in our fragment function, we will be calculating the distance to the center. So for each pixel, we calculate the distance to the center and we therefore define a radial gradient or something like a circle. So here we are doing the same. We are calculating the length of each pixel from the center. So the length of this pixel will be the distance from the UV center because we are in the UV space right now. So let's quickly visualize this distance from center and you will see it is a gradient like this. Oops. Yes, it is a gradient, but it's too faint. So let's add it to emission instead of the albedo. So you see, this is a gradient. Now the second step is to assign some colors to this boring ass gradient, and we quickly define uniform variables to find our colors, and we, instead of just directly putting the distance from center, we color this gradient here and we then assign the color to the emission. So let's quickly use the mix function to apply colors to the gradient. Now one thing that I missed earlier is that we need 3 kinds of colors in our specific case to add more variation to the shader effect. So I missed the color dark, so let's quickly add here uniform effect for color dark. Now we have 3 colors and we need to quickly assign this color channel to our emission, so we will have hopefully a good color gradient like this one. Now let me explain how it works. Basically we have defined 3 colors: color dark, color light, and color mid. First of all, we will mix the color dark and the color mid based on the distance from the center. We scale it to make it more pronounced, but it's just distance from the center. So as the distance from the center changes, the color gradient changes, and then we mix the existing color to the color light, again based on the distance from the center, but with a transforming function that applies it above certain threshold. So we see instead of the linear gradient, we have a linear gradient going on and then another layer that suddenly makes it more brighter around the corners. Now this is not so much, we can say, pronounced here because we have not added noise, but when we will add noise will add its own variations and you will clearly see effect will be much more visible. Now let's quickly add some noise. So for this we add a noise texture sampler and we add noise scale so we can control the size of the noise, and so let's integrate it here. So first of all we define the UVs, which are just built-in UVs that the Godot gives us access to with some scaling applied, and then we sample the noise texture with these scaled UVs, and finally we assign it to a pattern, a variable that we're going to use just later here. So instead of using the distance from center directly, we mix it with the noise pattern. So for this we can do something like this. Let's add both of them and divide by 2 like this and like this. Yes, and copy the same thing here. So we see there's some sort of noise, but let's assign the noise first. So you can see it looks a bit good. Let's also assign the albedo channel to albedo color so that it might affect the output and make it a little bit different. Now let's add some motion to the noise. It's too static, So let's add a variable for the portal speed and the direction of the scroll. In the fragment, let's add time. Now for the noise, instead of directly using the static UVs, first of all, let's define the UVs that are animated with time based on the scroll direction and assign these UVs to the texture sampling. So we will see the output will have kind of boring motion, but we'll later work on it to improve it. Now similarly, add the second scroll direction and the strength of distortion. This is to kind of add some variation to the effect so it doesn't look too static. So let's use these. So let's quickly add the second layer of noise, and it's just the difference in the UVs. So we are taking the same scale UVs and we are applying the different scroll direction, and also we are distorting the second UVs based on the noise that we calculated above, and we multiply its distortion strength to kind of amplify the effect. And now this raw pattern will use both noises averaged out, so we can just do divided by 2 instead of multiply by 0.5, so it's same anyways, it doesn't matter. Now so far, if we change the variables, we can see somehow it looks a bit like a portal. We can change the distortion strength and we can play with it, but it's still not that good. But let's continue. So the next thing we're gonna do is to make this raw pattern a bit sharper. So for this, we take that boring raw pattern and we use the smooth step function, keep the steps between 0.2 and 0.8, and so now the values, instead of changing very slowly and giving the very faint effect, they give a bit amplified effect. If you're confused about the smooth step function, let me explain it in an easier way. So you have a standard step function that looks like this. So it is a step. There is some value here, like we can say 2 and value 3 here. So we are stepping, we are certainly changing our function's output. Now what the smooth step does is it smoothens these edges. So instead of sharp decline, it makes it like this and like this. Or in the more clear version, it looks generally like this. Now the sharpness of this part depends on the values that we are giving. So when we use this, instead of that boring ass noise that looks like this, now our function looks like this. So it kind of amplifies the effect and it looks good. Now the next step is to add the spiral effect. So far we are just dealing with the linear effects. So let's add the spiral effect. For this we add the strength of the spiral, and for the spiral we need to calculate the angle of we can say distortion of rotation. What spiral really means that as we go away from the center, our direction changes like this based on some angle. Let's quickly add this spiral effect, and for this first we need to calculate the angle that is based on the distance from the center. So as we go away, the value of angle changes, and it depends on the spiral strength as well as time. So the spiral effect also depends on time. And then what we're gonna do later is to transform the pixel, any pixel, based on the rotation matrix. And to construct the rotation matrix, we need to calculate the sine and cosine of our angle. So let's quickly create the rotation matrix. It's kind of a simple linear algebra, and the concept is something like if we are going to multiply our pixel position in UV space with this rotation matrix, it will kind of rotate the pixel based on this angle, because this angle was used to construct this rotation matrix. Now if I explain this concept in this paint, it looks something like this. For example, if you have a point which is 1 in x and 0 in y, if you are to rotate this 90 degrees, what will be the new position of the point? It will something be like 0 at x and 1 at y. You can visualize it like this. So for example, you have this point that lies on 1x and 0y. Of course, it has no height. Now when you rotate it and bring it here, its y becomes 1. Now it is 1 here, but its x becomes 0. So this is the concept that the rotation matrix I was talking about. This one it uses. Now instead of sharp 90-degree rotation, the rotation is somewhere less than that based on the angle. So the concept is kind of technically simple, but it feels a little bit difficult if we look at it from just these symbols perspective. So let's quickly calculate the spiral UVs. which are based on the multiplication between the rotation matrix and the position of each pixel. You can say this variable defines the position of each pixel relative to the center in UV space, and this 0.5 thing is used to transform or offset the UV space back to how it was initially, starting at 0 0 here and 1 1 here, because before that we basically subtracted 0.5 to offset it, so its center was here. Now we are offsetting it back by adding 0.5, so its center is back here. I mean the origin is back here. Now our scale UV will use the spiral UV instead of the standard UV. So let's paste it here, and you will quickly notice this beautiful pattern occurring, but it still isn't enough for us. So our objective is to make the portions darker towards the center and lighter elsewhere. So we need to add a radial mask, another radial mask, which will cause it to become darker as you approach the center and lighter as you go away. And that will work by controlling the intensity of the noise that we are sampling here. So let's quickly add the uniform for this mask's intensity, or you can say the sharpness of this mask, or in other words the power of this mask. So let's quickly add this mask after we calculate the raw pattern, because this mask will be applied to this pattern, and it's again same gradient based on the smooth step function, and it works by the distance from the center, and apply the power to the edge mask so we can control its you can say sharpness or intensity using that power variable. Now let's calculate the final pattern, which is based on the initial raw pattern and the edge mask. So edge mask will really be multiplying with the pattern to control its intensity at any place. Now in our color calculations, instead of using the raw pattern, we use the final pattern that we calculated. So you see another radial gradient has influenced the noise, and now it looks like this. We are much closer to the final output. Now one more thing is that we need to remove the dependency of the dist from center, because our pattern is already kind of including that factor through the edge mask. So we need to remove this, and we need to directly use the final pattern instead of any other thing like this. So see, the effect becomes directly dependent on the final pattern. Now let's add some more uniforms for the metallic and roughness, and this is pretty simple. It's just a standard PBR material behaviors. So let's quickly assign them like this here, and they have some effect on the output. And now let's play with the effect. That's all for today's video. So thank you so much for watching, and see you very soon.